just as the derivative of the position function is the velocity function, the derivative of the velocity function is the acceleration function. So you have s of t, the position function. Then we take the derivative of the position function, s prime of t, and we get v of t, which is the velocity function. Then we take the derivative of the velocity function, and that's called the acceleration function. That means we derived the position function 2 times. So we found s prime prime of t, or the second derivative of t, or s double prime of t, however you want to say it. These are ways that it is written. Because the moon has no atmosphere, a falling object on the moon encounters no air resistance. In 1971, astronaut David Scott demonstrated that a feather and a hammer fall at the same rate on the moon. That's so crazy just to imagine, because that would never happen here. The position function for each of these falling objects, where s of t is the height in meters at t seconds, is given by this function right here. What is the ratio of Earth's gravitational force to the moon's gravitational force? Remember, the Earth's gravitational force of a falling object is negative 9.8 meters per second. So, how do we find the moon's? If we want to find the moon's gravitational force, we have to find the acceleration of these falling objects on the moon, because the only thing that is accelerating the falling objects on the moon is literally the gravity of the moon, right? There's not even air resistance. S of t is negative. So now I'm going to derive s of t, which gives me the velocity function. Pop down, power down, negative 1.62 times t to the 1 plus 0. And now I'm going to find the acceleration function, the derivative of the velocity function, which is the double derivative of the position function, and we get negative 1.62. So the acceleration of a falling object on the moon is negative 1.62. The gravitational force of a falling object on the moon is negative 1.62, and they said already that we were in meters per second. So what is the ratio of Earth's gravitational force to the moon's? We're going to write that as a ratio, Earth's gravitational force over moon's, so negative 9.8 over negative 1.62, which is approximately 6.05. That's not meters per second, right? Because this is the ratio. So the ratio of Earth's gravity to moon's gravity is approximately 6. We have approximately 6 times more gravitational force here on Earth than on the moon. We're going to try a couple more examples with just finding higher order derivatives. So here's our notation. Once they get up to past 3, the third derivative, they start using numbers instead of little apostrophes, because at some point your eyes don't know how many apostrophes there are. We need to find the 6th derivative of this polynomial. Ooh, yikes. Let's start. F prime of x is equal to, pop down, power down. This is a 1. Okay, so 6x squared minus 10x plus 10. F prime prime of x. Pop down, power down. 12x minus 10. F prime 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 of x is 12. F fourth derivative of f of x is 0. Fifth derivative of f of x. What's the derivative of 0? That's 0. Sixth derivative sixth derivative of f of x is 0. All right, and let's try this one. They want us to find the fourth derivation of y with respect to x of sine x. Another way we could write this is that y is the function sine x, and we need to find y, the fourth derivative of y. So I'm going to do it that way. Y prime is cosine x. Y prime prime is the derivative of cosine x, which is negative sine x. Y prime 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 is the derivative of negative sine x. So negative 1 times sine x, you have negative 1 times the derivative of sine x is cosine x. And y, the fourth derivative of y, is negative cosine x. Okay, so the derivative of cosine x is negative sine, and that would be negative sine x, which is just positive sine x. So the fourth derivative of sine x is sine x. Interesting.